Forget frequently asked questions, common sense, common knowledge, or Google. How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5% go above and beyond and become very good at what they do. But only 0.1% are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in fields such as sleep science, cancer, stem cells, ketogenic diets, and more. Get ready. Here come the geniuses. This is the Finding Genius Podcast with Richard Jacobs.
Hello, this is Richard Jacobs with the Future Tech and Finding Genius podcast series. I have Andreas Baur. He's a medical doctor, PhD professor. He's at the University of Regensburg, and we're going to be talking about his research, which involves currently extracellular vesicles, EVs. So, Andreas, thanks for coming. How are you doing today?
Thanks for having me.
Yeah, I've spoken to a number of people in the EV world. What's your focus within it?
Well, we focus particularly on the function of EV in patients in plasma. So I guess my lab is one of the very few who systematically analyzes these vesicles in patients. And the reason is because I'm a medical doctor, I see patients, so I have easy access to this material, which is absolutely paramount for this kind of work. And we simply ask, why are they there? When do they increase? What are they doing? What is their content? And what is their relation, their connection to disease development? These are basically the questions we're asking.
So you still see active patients? You have
yes.
A couple days a week? Okay.
2 days a week I see patients mainly with melanoma, but also with general dermatological diseases. And the rest of the week I'm here in my lab. I have about 5 to 10 people. We do translational research, but also a lot of molecular biology. And with this sort of technology, we try to address the questions I mentioned. And then particularly where are these vesicles coming from, where are they secreted, and what can we learn from them?
So you said that they're observed in the plasma. You mean in the blood plasma of people, or in let me saliva? Or what?
Right. Let me just get a little bit back in history, so to speak, to understand where I'm coming from. So I started out in the 90s as a basic researcher on HIV, on molecular biology, on of HIV, and particularly on one protein. It's called the NEF protein. And in the early 2000s, this was all done in vitro. We found that the virus, the HIV virus, is inducing rather potently the secretion of these vesicles in vitro from infected cells. And this got me very, very curious. And I said, why is the virus doing that? And we looked into what's in these vesicles, and we found a lot of things, including proteases. And I said, why are proteases in there? And from there, I went, since I was in the clinic, I went to patients, or the plasma from patients, and looked whether I see the vesicles not only in vitro, but also in patients. And yes, they were there, and they were really strongly elevated in numbers over controls. And from there, I got more and more involved and interested in why are there vesicles in plasma, and why there are more in HIV, and what do they contain, and what does it mean at all? And the basic finding we made was that the concentration, the content of these vesicles correlated very well with the stage of the disease, with the pathogenesis and the number of CD4 cells. So there was something very important about these vesicles. And at the same time, I was wondering whether there are vesicles only in HIV patients. So I looked in many other patients, cancer patients, but also in patients with neurodegenerative diseases or in acute infections. And whenever I looked, I found them in huge numbers. And from there, I started to have more and more interest into these structures and to understand why are they there and what are they doing.
So I've heard that cancer cells, I know regular cells put out EVs, but I've heard cancer cells seem to put out a lot more than regular healthy somatic cells. But you're saying that viruses also will induce our somatic cells, once they're infected, to spit out a lot more EVs than normal?
Yeah, in principle, you can say that every cell that is somehow activated, whether it's because it's a cancer cell or whether it's because there's a virus that transforms a cell, these cells basically secrete larger number of vesicles. The reason is not entirely clear yet, but basically it is a response. In principle, it is a response to a signal. Usually it could be a danger signal, it could be an activation signal. And in cancer, this seems to be important for the cancer cells for reasons that are not entirely clear. And the same is true for HIV or for viruses. They induce the secretion of these vesicles, most likely for their own good, means they stimulate viral replication. Now, behind all of that, there seems to be a system, because the human body, even if we are healthy and have no virus and no cancer, we still produce vesicles. So the question is, why do we do that? And who is doing that? And if I put together what we found, it seems like there is one organ that is a major producer of vesicles, and that's, in our opinion, the liver. And the liver is, so to speak, the mother of all organs in our body, and it sort of screens the blood permanently. And as soon as it encounters or senses a danger signal, it basically secretes in higher numbers these vesicles in order to fix a problem or to fix the perceived problem. This is sort of our basic idea. It's still an hypothesis. And these vesicles...
Quick question.
Yep.
A quick question there. Have you looked upstream and downstream in the liver to see if the liver, as part of the cleaning, eats up a whole bunch of vesicles that would be present in the blood?
No, the liver... We haven't looked into that particular question. We only know that the vesicles that are spit out by the liver are targeting the immune system, particularly precursor cells. So the liver is giving these cells a message in the human body saying, listen, we've got a problem here. Please look out, take care of it. And that's what we think is the basic mechanism here. Now, it seems that viruses exploit that system for their own purpose. For example, they occupy a cell, they spit out vesicles, and they then activate, for example, T cells or the immune system. And this, again, is an advantage for a virus like HIV who lives in the immune system. Now, why cancer cells do that? There are theories out there that they sort of prepare their metastatic niche, so they sort of fend off the immune system, they defend themselves against the aggression of the immune system, or they prepare a niche where they can survive and basically proliferate on a low rate and sort of cannot be cleared by the immune system. And yeah.
In blood, I would think that there are many different types of vesicles and countless millions and billions of them. How do you separate out the contents of the vesicles without mixing them in such a way as where you couldn't tell what they're composed of?
It's a very, very good question, and that's basically one of the big problems in this field, that we have lots of vesicles with about 10 to the 10th per milliliter per plasma, but we don't really know where they're coming from. Now you will probably ask me, how do you know they come from the liver? Well, we see in certain conditions that the liver acute phase proteins are increasing dramatically in these vesicles. And since the liver is probably the only organ doing this more or less on demand or on activation, we assume that many of these vesicles come from the liver. But there is additional evidence which we have gathered that all points to the liver at least as one major secreting organ. This does not, but we know that there are vesicles also coming from platelets, from immune cells, from dendritic cells, maybe also from activated T cells. So in summary, you're correct. These vesicles come from very different cell population organs, and we at the moment have no means to discriminate them.
I thought people were using like ultracentrifugation or, with them.
Yeah, that's the standard method, to use ultracentrifugation. It's not a particularly good or efficient method, but it works perfectly well if you, for example, extract vesicles from plasma of patients. And then once you have them, you can analyze them for what they contain. And there we see huge differences in between, let's say, a healthy individual and someone with an Alzheimer's disease or HIV or a cancer, an acute cancer, a relapsing cancer, or a cancer with a low relapse probability. We see there huge difference sometimes, and we use these differences to discriminate diseases. And eventually, and at the moment, we're trying to establish a test system that has a high predictive value, not only for specific disease, but also for specific disease state. And this works very well. So this is at least one of the goals that we have in the lab to use this information that is in these vesicles for diagnostic purpose.
Oh, so what kind of conditions would you work to diagnose? What are some of the first few?
What kind of conditions we diagnose?
Yeah, which ones would you want to, to go after all of them?
Okay, let's say you, I don't know how old you are. Let's just say you're 45 or something, and you want to know whether there's any disease coming up in your sort of aging body, whether you will develop a cancer or will develop Alzheimer. Then I could look it up. I could extract your vesicles. I could analyze the patterns of factors I find there. I could compare it with other patterns that I already have in the data bank, and I could come up with a diagnosis saying, well, it's possible that there is something, that there's a cancer growing, or that you have an acute infection, or just whatever. How do I know that? Well, because we have so far screened almost 500 people, including healthy controls and individuals with different diseases. So we gained a lot of experience in doing that. And not rarely, in apparently healthy individuals, we found specific patterns, and we send them to the doctor, and eventually they would find something. And so we knew that we were correct. And so we developed a test system out of that, and this is currently, as we speak, it's funded by the German Ministry of Research to develop a test system that is more predictive than test systems we have at the moment, specifically for cancer.
So, okay, what do you think is going to be the big breaking point? Is it in isolating the EVs and being able to analyze them? Is that the holdback, or is it? Some researchers I've spoken to seem to know that inside of EVs, there's proteases, there's small RNA, there's a whole bunch of things. Is it characterizing their cargo? Is it again being able to isolate them effectively? Like what are some of the major goals for your lab?
The major goal of my lab, with respect to diagnostics, we have also other branches of our interests, is to we have teamed up with people from the hardware industry to automatically isolate plasma vesicles in a defined manner, standardized from plasma, and then use the purified vesicle for basically two types of diagnostic tests. One test is measuring enzymatic activity in these vesicles. What we discovered and published is that these vesicles contain sometimes a whole array of so-called proteases. And the type of proteases, the number of proteases, their activity correlates sometimes very well with disease development. So this is one test system. It's very sensitive and it's very reliable. And then there's another test system that basically analyzes the factors that are found in these vesicles. So in individuals that are healthy, let's say in a young individual that has no disease and nothing, you basically will not find a lot of these factors. Let's just leave it like that for the moment. But as soon as a condition develops, a disease, acute infection, a cancer, whatever, these vesicles fill up with an enormous amount of chemokines, cytokines, soluble ligands, and other proteins, which you can measure and quantify. And all of these factors basically make or generate a pattern, a certain pattern. And this pattern, at least I will predict that is very, very helpful and very predictive for human disease and clinical condition. And this is going to be not only from our lab, but also from other lab. I know that other labs work also on that. This will be one of the future diagnostic tests in medicine.
So what do you think will be the differences between EVs from healthy cells versus EVs from diseased cells? Like when you spoke about the virus example, do you think that the virus is causing the cell to put out EVs to help the virus spread, or is the cell itself?
Well, in the case of the virus, yes. Well, let's assume a situation. Let's say you are in a cramped bus with many people having, let's say, a coronavirus, which is very is an absolute recent topic. And you inhale it. You inhale little bubbles with viruses. This go into the bloodstream, and the first one to notice will be your liver. Your liver has specific receptors for these foreign proteins, DNAs, RNAs, and will immediately spit out vesicles in order to alert the immune system. In this period, the number of your vesicles increases sharply, and they contain all these factors I've talked about in order to alert the immune system and fight the intruder. That's the basic concept that we believe in. Now, as I said before, viruses that come through evolution know this, and they use this system for their own purposes. For example, let's say there's an HIV virus. HIV needs TNF to stimulate T cells. Now, in order to produce TNF, you need a certain protease, namely ADAM17. Now, the virus somehow knows that ADAM17 is produced in the liver and secreted by vesicles. So what does it do? It somehow stimulates these hepatocytes to produce exactly this protease, which then is incorporated into the immune system, activates ADAM17. ADAM17 activates TNF, and that helps the virus. So what originally is meant as an immune defense system is taken or exploited by the virus for its own activation. At least that's what we think is happening.
That's amazing. How could it, it's crazy. I don't know how I could know that.
Yeah, and then from there is a short step, not such interesting branch or step to disease development. Now, let's go back to our example with the coronavirus. You got this little droplets, your system fought it, and you don't get sick. But let's assume that this machinery that has been turned on is not turned off anymore for whatever reason. Let's just assume it for a moment. Then this continuous vesicle production which has all these highly active compounds in this as a content may produce conditions or disease conditions that could lead, for example, to depression or allergies or fever or whatever. So this is where the system more or less, or this vesicle system that is a system to prevent damage, could by itself induce damage. And this is what we think is happening when we look, for example, in neurodegenerative diseases, in chronic infections, in allergies, in disease conditions that at the moment we don't have so much explanations for. At least this is what is the summary of our studies of the last 4 years. So in other words, when we look into these diseases, we look into the vesicles, we find high levels of these factors, and at least in some instances, we could demonstrate that there is a connection to the disease or to the development of it. Particular, and that's very interesting, that will be the future big topic in neurodegenerative. So you may have heard that, for example, endogenous depression is caused by inflammation, that the inflammation is coming from the body and somehow finds its way into the brain. And we know, we have evidence, and we think that this is conveyed or induced by excess vesicle production that contains inflammatory factors, as for example, these activated proteases.
So do you think that EVs are more used in customary cell-to-cell communication, or is it not often used and it's more in disease states that it comes out?
Yeah, that's actually how the field started out. The field started out thinking, well, these EVs are just there to exchange information. But this is not wrong, at least in my opinion. But it's also not completely correct. These EVs are effectors. These EVs are tools to do something. So someone is telling someone else to do something. And in our opinion, it could be a dendritic cell, it could be the immune system, or it could be the liver that senses something, a danger signal, for example, and then wants to instruct other cells to do something. So it's much more than just an exchange of information. It's basically, it enables events to happen in distant organs, for example. So because these vesicles can travel within a heartbeat, literally a heartbeat, from the liver to the brain, and not only provide information, but also tools that cells in the brain can, for example, defend themselves against an intruder or something like that. So it's much more complex. It's not just as simple as an exchange of information.
Any big breakthroughs that you sense are close at hand in the next year or two with your research?
Absolutely. So we, first of all, the first breakthrough will be in predictive diagnostics. I'm absolutely convinced that what you see in these vesicles will give you a prediction ahead of clinical development. Why do I know? Why do I say that? Because the immune system, the innate immune system, is the first one to know if anything happens, sometimes within minutes. So if you can basically read the message in these vesicles, you know ahead of the clinical symptoms that something is coming and you can intervene early. So this is the first breakthrough. The second breakthrough will be what I call some sort of vesicle interference therapy. So in other words, if you have disease conditions where there is an excess production of vesicles that are detrimental, there are ways to interrupt. We came across a compound that was developed in the 60s and 70s that is a very, very potent inhibitor of vesicle secretion. And since this is a licensed drug, we tested it already in patients, and the results were really encouraging and sometimes close to sensational. So we are currently trying to set up a clinical trial, which is not that easy nowadays, to prove that point. But I would predict that these kind of treatments and diagnostics will be a big part of future medicine.
Well, very good. Well, Andreas, what's the best way for people to learn more? Maybe look at some of your papers and see what your lab is doing.
Well, that's certainly one way, but it's, this is a very complicated field for someone who is, let's say, not a knee-deep molecular biologist or clinician. It's at the moment rather difficult because the field is still growing. It's growing very fast, and there's still a lot of things we don't know. So just be patient. The news will come and also will spread into the popular press, and people will, I think, in the next 1, 2, 3 years, learn much more about these vesicles. And there will be publications more in lay language that people can understand. Right now, it's still a small field. It's still very scientific, molecular. And but if you if an interested reader has background knowledge, you can certainly read review articles that are out there already. But what I told you is still more the future than current knowledge.
Okay, well, very good. Well, Andreas, thank you for coming. I appreciate it.
Welcome. Thank you very much.
Forget frequently asked questions, common sense, common knowledge, or Google. How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5% go above and beyond and become very good at what they do. But only 0.1% are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in fields such as sleep science, cancer, stem cells, ketogenic diets, and more. Get ready. Here come the geniuses. This is the Finding Genius Podcast with Richard Jacobs.